Over the recent while, I've been working with Kyatchi Carbon to develop a splitter range to sell. The aim was to build different levels of downforce within manufacturing constraints. While the basic splitters aren't pushing limits, these tend to be cost-effective designs. The main work is extending the upper limits of performance, and here I'm going to walk through how this was achieved. Working with Jared from Kyatchi Carbon also means I have an affiliate link, which I receive a portion of the sales from the splitter. There is also a code that you can enter to get a discount or additional titanium pucks. This would be a great way to support the channel and a local Melbourne business. All the details are in the description. So this video will go through how splitters produce performance, starting off with entry-level splitters and building a knowledge base through levels of accessibility to a unique and innovative high-end splitter that we have developed, which is available for purchase. The basic premise of a splitter is to provide an aerodynamic surface under the front of the car to produce downforce. As the car pushes through the air, there is a high pressure zone at the front where the air forms a stagnation point. Outside of this zone, the air begins to accelerate, lowering pressure around the front edge, top, side, and under the vehicle. Top and side, you want to minimize the low pressure. The top, because it creates local lift. Under the vehicle, it can be obviously beneficial because it produces a pressure gradient used for downforce. In the most basic form, a plywood splitter will trip the air over the leading edge, forming a separation bubble, but also a decent level of low pressure. It is dirty downforce, but it is there. Over this flat surface, the pressure gradient will end up recovering across this horizontal plane, which is the downforce. The difference between a plywood splitter and the one you would pay money for is weight and the treatment of the leading and trailing edges. With increasing loads, a plywood splitter starts to get heavy, whereas a carbon one is filled with foam, so adding thickness for strength doesn't add as much weight. Adding thickness also means a radius that decreases the pressure gradient over the leading edge, making the device more efficient for one because there is no adverse pressure gradient, but it also allows an increased angle of attack, thus increasing not the pressure gradient but its size. So the volume of the pressure field is larger, which means higher downforce. The next step in increasing downforce is increasing the pressure field by increasing the size of the splitter or its effective size with end plates. Nothing changes apart from the volume of affected air, that is, the mass flow rate. Again, using a plywood splitter, weight becomes increasingly impactful. There is a practical limit to the surface area and volume. Speed is a product of performance, so the only way to increase performance is to increase the pressure gradient inside the workable volume over the surface. Commonly this is done by adding diffuser tunnels. There is nothing new in that, though getting them right is a process because there is a couple of parameters that we are working with. It's all about managing the pressure gradients and the momentum of the flow field. Pressure gradients can be divided into two categories, surface and flow field. Though they are connected, literally, surface gradients determine flow separation, whereas the flow field dictates the problem space. Surface gradients is also downforce. High pressure gradients means more downforce. Adding tunnels accentuates the pressure gradients by expanding the peak low pressure zone after the leading edge. The mouth of the tunnels is where the air accelerates over the kick radius, expanding into the diffuser. Setting the tunnel's mouth a little after the leading edge links the pressure zones, expanding the size of the very low pressure. After the tunnel mouth, the air will increase in pressure as it enters and approaches the wheel well. Pressure recovery over this surface means managing the pressure gradient to avoid backflow and introducing high pressure onto the tunnel surface, reducing downforce significantly. A typical high-performance universal splitter has these tunnels exiting into the wheel wells. Though the wheel wells are low pressure, lowering them further will increase the performance of the splitter. Running a splitter with tunnels is usually coupled with modifying the wheel well because this is the performance ceiling that the splitter is operating under. That is, it's one end of the flow field, the other is the front of the car, with its mentioned high pressure zone, normally fitted with an air dam across the top of the splitter and in front of the bumper. So the high pressure gradient of the flow field is the front of the car and the wheel well. However, there is a trick that I haven't seen on production-derived vehicles, though it used to be common and not surprisingly outlawed practice in Formula 1. It's ducting air between pressure fields. Basically, hacking the pressure field with ducting. Using the Bernoulli principle of high-pressure, low-velocity air present on the top of the splitter at the front, it's ducted through a decreasing cross-sectional area to exit at the splitter's tunnel's truncated trailing edge. This does a couple of things, but the main one is lowering the air pressure at the trailing edge of the splitter tunnels and thus increasing the pressure gradient of the flow field. In this configuration that is available from Kyatchi Carbon, it increases the performance, or downforce specifically, by about 12.5%. This configuration is determined by manufacturing and cost. I am assuming if you want to pay more for an increase in performance, Jared would or could be persuaded. Anyway, the aim of this exercise was to produce the highest downforce splitter available on the Australian market. According to publicly available claims, this was achieved.